The Wright brothers made history in 1903 when they made the first true powered flight. Their achievement was made possible by the light and powerful engine that they designed and built themselves. This video uses a 3D model that I created using information that I found on the internet to describe and explain how this innovative engine works. It's a 4-cylinder, 4-stroke water-cooled engine. The cylinder block is aluminium to reduce weight, and the pistons and liners are made of cast iron. The crankshaft was machined from a solid piece of steel. An unusual feature is that the combustion doesn't take place in the cylinders, but in a separate combustion chamber, which is screwed onto the top of the cylinder liner. I've shown the engine upright with the cylinders vertical so you can see all the parts better. But as you can see from this 1916 recreation, it's actually a horizontal engine. You can see the legs on the back, which is actually the bottom. This is the combustion chamber, which is the heart of the engine. The slots are to allow the exhaust gases to escape. This is the combustion chamber with the outer case removed. There are two valves inside, the exhaust valve and the inlet valve. There are also the contact points which create the spark when the moving lever taps the fixed anvil. Here is a simple engine model with most of the parts removed. You can see the cylinder, piston, combustion chamber, valves and spark plug. The blue represents the air-fuel mixture. We can start with the piston at the top of its stroke. The combustion chamber contains a mixture of fuel and air, and both valves are closed. A spark from the contact points ignites this mixture and it expands, pushing the piston down and producing power. When the piston reaches the bottom of its stroke and starts to return, the exhaust valve opens, thus the hot gas escapes the atmosphere through the slots in the side of the combustion chamber. When the piston reaches the top, the exhaust valve closes and the inlet valve is opened by suction as the piston descends, thus drawing in the air-fuel mix. When the piston reaches the bottom and starts to ascend, the inlet valve closes. As both valves are closed, the air-fuel mixture is compressed. A spark ignites this mixture and the next cycle begins. The fuel system is very simple. There's no carburetor. The petrol simply trickles into the air inlet and is entrained into the air being sucked in by the engine. The fuel comes from a small overhead tank and the flow is regulated by hand using a tap. The Wright brothers used a tap from a household gas light. When I remove the cover, you can see that the air and fuel flow around a circuit which encourages mixing before entering the inlet manifold. The warmth of the engine helps the mixing process. The inlet valves are held closed by light springs and opened by suction as the piston descends. The voltage for the spark is provided by a 10-volt magneto driven from the flywheel. They may have adapted a magneto from a hand-cranked telephone, and I found a YouTube video of a guy overhauling one, so I based it on that. The armature rotates in the magnetic field created by the horseshoe-shaped permanent magnets, thus generating a current in the copper winding. The engine was started using a battery before the engine was rotating fast enough for the magneto to take over, but the battery wasn't carried on the flight. The magneto is connected to the insulated spark plug terminals by a copper busbar. Now to the way the timing of the spark and the valves opening and closing is controlled. I have removed the cylinder block so you can see it more clearly. The camshaft, coloured red, is driven from the crankshaft by a bicycle chain. I have modelled the type of chain which was typical at the time. Because it's a 4-stroke engine, the camshaft turns at half the speed of the crankshaft, so there are twice as many teeth on the camshaft sprocket as on the crankshaft sprocket. The cams on the camshaft push the rockers, which push on the exhaust valves, so opening them against the spring. A separate ignition shaft is driven by gears from the camshaft. The reason it's separate is so the spark timing can be adjusted. This is described in detail later. The cams on the ignition shaft lift a lever which causes the spark arm to tap the spark plug body. Let's take a closer look. The mousetrap spring pulls the lever down and the steady spring stabilizes it. The cam is a bent strip of metal, so the lever drops off quickly. The spark should occur just before the piston reaches top dead center to allow the air-fuel mix time to fully ignite and build up the pressure. The amount depends on the engine speed, and so it needs to be adjusted to suit. This little lever does that. The gear on the ignition shaft isn't fixed to the shaft, but can slide along it. A cam fixed to the lever pushes it along the shaft against a spring. The gear uses a pin in the helical slot to drive the ignition shaft, and so as the gear slides along the shaft, the ignition shaft rotates relative to the gear, thus advancing or retarding the spark. The engine uses splash lubrication. There are no oil galleries to feed oil directly to the bearings and the other moving parts. Oil drains from the cylinder block into this manifold. Remember that the engine is mounted on its back, so this is the lowest point. This pipe takes the oil to the gear-type oil pump, which is driven by a worm gear mounted on the camshaft. In a gear pump, the oil is carried around the outside by the gear teeth. It can't get back through the mesh gears, and so is forced into the outlet pipe. The oil is fed to a hole in each of the cylinder liners and lubricates the pistons and cylinder bores. The rest of the moving parts are lubricated by the oil splashing around before it drains from the crankcase and is recirculated. The engine is water-cooled. There is no water pump. The cooling system relies on convection to circulate the water between the engine and the small overhead radiator. The radiator was made from the speaking tubes used in apartment buildings at the time. The water entered the engine block through a pipe at the bottom of the engine and exited by two outlet pipes. That ends the description of the engine. My main reason for modelling the engine was to learn 3D modelling, animation and video editing. I used material I found on the internet. The original engine was made using rough sketches which weren't kept, and all the parts except the engine block have been lost. The engine was rebuilt in 1916, although it's not clear how accurately. I found some photographs of that, and some parts that have been made for modern recreations of the engine. This is the main drawing that I used. It's widely available on the internet, but it was probably made from or for the rebuilt engine, certainly not the original. I modelled the engine, animated it, and made the procedural materials using a program called Blender, which is available free of charge on the internet. You can learn Blender using the many free Blender tutorials on YouTube. I started with modelling a donut using the excellent course by Andrew Price, who goes by the name of the Blender Guru. I edited the video using a program called DaVinci. The basic version is free, although I bought the full version for around $250. Thanks for watching. I hope you found it interesting. We retired to Switzerland about 7 years ago and make videos mainly about our travels, but also anything else that interests us, just for fun.